and these green dots are comets. This is Halley's Comet, and the other one, which is somewhere over here, is Comet Wortman. This is the main asteroid belt.
Just to give a perspective, this is actually an advanced functions final project. So this, if you take advanced functions, precalculus advanced functions, it's probably a year or so. This is how you're finishing your spring semester. So she's already doing.
Oh, and one thing, I added in the names of everything here, so you can't see it when it's black, but. And now you can see all this. And the planets have some realistic...
Ladies and gentlemen, Dr. Daly.
Okay, so my project is about perspective in like architecture and photography and that type of thing. So the first thing I did was did sort of like a construction of how our eye sees things and why when you're driving down a road, the telephone posts at the end of the road look smaller than the ones right in front of you, and the way that you can think about it.
Actually, can I stop you? Think about that question. Why objects at a distance look smaller? I mean, if you're far away, that doesn't mean you shrank, right? Have you ever thought about that? Persons don't get, they're not smaller themselves. They look smaller. So he's explaining that with a really very clever diagram.
So there's supposed to be an eyeball over here.
Let me actually, if you scroll up here, you'll be able to see that, maximize that one right there.
Okay, so here, if this is your eye, and you're looking through a pane of glass, and this is the telephone post, even though the telephone post is always staying the same length, the light, the lines represent the light reflections off of the pole. So you can see that if you move it, the red line here is getting bigger.
Show it there. They're not seeing.
The red line there is getting bigger if you move it closer, and smaller if you move it further. So that's how your eye is going to see it.
Okay. So light ray from the top of the object, light ray from the bottom of the object is coming to your eye. That's how you're seeing it. And what intersects the canvas, right? That's what the size is going to be. So imagine a glass canvas.
And then once you get all the way to here, it becomes the same size. You can sort of see how that works.
Very good.
Line patterns on the top of it, and we can show it rotating again. So it's done. It's pretty much done the same way as the triangle is, but obviously instead of 3 points, you have 5 points, and then
Can you tilt it?
Can I tilt it? Yes, I can.
There's a show tilt tool. Look what's going to happen. So you're able to change that viewing angle. There's a place beyond which the eye won't be fooled anymore. So it's an illusion you create.
When it would naturally flip if it was really. And then, I guess that's
beautiful.
That's it.
Beautiful.
Malika
Mehta.
My project was basically using hypnotic spirals to connecting them to dance, and that proved to be a little difficult, but I think I did it. I also wrote a story relating, it was a fiction story about how geometry and dance come together, and how Indian gods played a part in this. Completely fiction, but okay. Yeah, so I can see the dance now.
Ladies and gentlemen, Dr. Paul Kumbi.
So for my project, I wrote a program from scratch which would facilitate the exploration of Euclidean geometry. So for those of you who've seen Sketchpad, something along that line. So what I have here is the circumscribing circle construction, which I built a minute ago. And so one of probably the biggest challenge about this was that I had to come up with a way in which objects that we use and write down on paper could become objects that can be put into a computer, because there's a certain amount of creativity involved with laying geometry out on paper, where we assume things about what we're doing that a computer wouldn't necessarily. So I had to come up with my own definitions of basically what a line is, and quite thankfully we know that lines have to be based on 2 points, so I can use that and say, okay, then I'm never going to have a line without 2 points, so therefore I can define a line in terms of having a start point and an end point. And so building up from there,
I just want to make sure people heard that correctly. You're not looking at Geometry Sketchpad. You're aware of this, right?
I didn't know that.
This is from scratch. So he's basically rewriting Sketchpad or his version of Sketchpad. So this looks like the interface of Sketchpad. You're not looking at Sketchpad right now. This is all Sketchpad.
so I added a few things. This is actually a demonstration of a few more of the functions. It's quite interesting when you try to go between coordinate geometry and the geometry we do in class, because you end up having to deal with situations that are different. You end up with different setups. So you end up with cases where slopes are greater than 1, or greater than 0, slopes that are less than 0, when slopes get undefined and slopes get 0. So for every one of these functions that I come up with, perpendiculars, parallels, intersections, I had to come up with my own way of handling these different exceptions. And I actually caught one this morning that I hadn't come up with already. So work in progress is a quite accurate description of this. It's quite interesting because when we deal with numbers and writing things down, we can talk about them as being exact, but you can never quite get exact on a lot of the fractions we deal with. But since the computer doesn't compute it in fractions, you can get in situations where you end up with rounding errors, like this. But and because this is my program, I got to put stuff in it that Sketchpad wouldn't necessarily have. So one of the things which I decided to add was a centroid function,
One more.
which
Fine.
creates creates points which are the average of the x's and the y's for this particular set of points.
So it's the generalization of what, basically? Like a midpoint. Think of a midpoint.
Yeah.
A midpoint is the average of 2 points. So this is basically generalization of that. If you have endpoints, it averages all of the endpoints, the x and y coordinates.
And there's an interesting property, which we'll see here in a moment, and that is that if you select a number, if you create the midpoints going around for every one, selecting all the objects, and you select a total of 1 less than the total number of points, you end up getting a mirror of the object you made the centroids from.
One more. The other side also. The other side doesn't match also.
Points that are not representing it in the flipped version. So there's math here, and I've just briefly begun to think about what kind of connections you can draw from this and how that works and what the math behind it is. Is there a branch of theorems that deal with when you have averages?
The Quimby theorems that is still to be written. Paul, I want you to start wrapping. We have half an hour. I want to
Yeah.
make sure we have, like, everybody's not gonna sort of go to their posters. Do you have any concluding remarks with which you wanna, or anything? Because you're gonna have your stand, and people are gonna
Yeah,
still come and
yeah.
visit you. But I want to make sure
I
everybody.
have a remarkable level of respect for whoever it was who programmed Geometry Sketchpad. Just having gone this far and with the basic functions, it is quite remarkable the pieces Dr. we get to use. So Sketchpad is a very sophisticated tool, and it's really interesting that we get to use it on our level here.
You added the function, but you didn't know this was going to happen.
Yeah, I know that the n minus 1 had it.
Tell me about, is this a double test ring?
Yeah.
And what's interesting is that the things aren't touching, but these three don't touch. Down these two aren't touching.
Yeah.
For the one tracing, there's a segment and there's the big point.
There's some that like don't look like actual rings, but they fit the definitions and they're considered rings. Most of them. And so I based my work off of Tony Diaz's work last year, and he did single Diaz rings or test rings. So I did double test rings, which uses 2 polygons to go in the ring. And so this explains like the fundamental theorem where the pinpoint segments of the polygons have to join at an angle that can create a regular polygon.
Beautiful.
A teddy bear out of I had the pattern, but it was just looking at the pattern how like it creates like why it is the way it is to like make him look curious. And one of the things that is interesting is like to create him like a belly to curve outwards. And ends up having it's like that, 2 sides like that, which are 2 curves. So when you put it together, it ends up curving out. And also, the more pieces that you have, which is like here, the more pieces of fabric you have, the more you can like control the shape. With like this, with 1 piece, you can't really control it. With 2 pieces, you can control like the width pretty much, but you can't really like control the height of it too much, like with his arm and stuff, and simple stuff like that. And then with 3, you can control the height of 1 side.
Yeah. And what about, and that's just the neutral for these as well?
So then there's 3 I just kept
Kevin?
And how long did it take to make this whole pattern?
Maybe an hour.
Tell them about
I had to bust
This one, okay. Well, first I made a circle, and then I put a line from the midpoint to the outside, bisected the segment, and then used the bisect the point that bisects the segment as the center. I'll put a circle to the center.
the way you do it.
Rotate that.
Alright, so for demo day, I decided I would construct Archimedean solids. They're very intriguing polyhedrons because they have the idea of a polyhedron, basically any shape that can cover a space, a 3-dimensional area. Why these are so interesting is because every vertice of a polyhedron that is an Archimedean solid is made from the same arrangements of polygons, similar to an Archimedean tessellation.
Yeah, so I made tessellations, which are basically groups of shapes that fill a space or fill a plane without leaving space in between. So like I looked at different kinds, like regular ones, special ones.
Okay, you tracing.
different.
He's
See. It's interesting because it'll actually create some more shapes.
Oh, that's quite different from the others. It's really very angular.
So you mean
And this one actually created a spiral.
So, yes, I'm getting pretty close.
Oh, I see.
Look at it
Okay.
up or down.
Okay, so it's probably will connect at some point because of the circular nature of it.
Both are the same. The distance between doesn't matter. But
oh really? It still makes the same shape?
yeah. And that was actually the only aspect of my project I was able to mathematically prove with the math I have right now. But the if you change the
Now it is feeding time by the creators of beautiful work.
Zero last year. So, dear journal, Cyril seems to have become threatened by my presence in the city. I hear more and more information every day of his dislike of my influence in the thinking of the people in Alexandria. I was willing to disregard the fact that his dislike of me was so strong. However, I heard some startling facts today. Rumors have begun to build about the true nature of what my study is. Cyril, as you might have guessed, has spread the information that I am a witch, studying black magic and that I speak with the devil by night. He's been spreading this nonsense through the city, and the people have become frightened, and they're calling for my death. I can hear screams in the alleyways, and the riots have begun to build outside my door. I do not know what to do, and I hope that this will pass, and that everyone can see the error in their ways. But the whispers of witchcraft are of concern, for I do not know how to convince the public of what their minds have been set on. I know not how to change their opinions of me. It would not matter, but something in the stares I get as I pass them in the marketplace tells me the angry eyes hold more than emotion. They want something from me, and I fear it is my life. And then in March of the year 415, the beautiful Hypatia was dragged from her horse-drawn chariot on her way back from the city of Alexandria's center. The Christian mob that attacked her were claiming to rid the city of all witchcraft and sorcery. She was taken into a religious temple and killed by shards of broken pottery, and then dragged back through the streets where she was burned at the stake. Yeah.
To interview a great local violin maker by the name of Bob Childs. And I also corresponded with a woman named Laura Risk who lives in Montreal, and she gave me a lot of my the physics backing that I needed since I haven't really done that before. And so, let's see. I guess I'll show you a short clip. I think I interviewed him, and it's just, you'll hear my question and his response.
I don't know, people need to reorient themselves. Like if you guys need to move, like last year when the master Chris O'Connell was performing, everybody like sat on the floor. He was speaking, we were like on the floor listening to him like this, okay? So don't be embarrassed. So let me.
Involved in your making of it, and he's going on to explain that there's a woman and she tried to derive some mathematical formulas to find like the quote-unquote perfect violin proportions, but he's explaining here that he thinks the most beautiful of the violins that have the best tone and whatnot are really made by hand, and there's like some sort of mystery that or love that goes into when a human makes a violin. So, can you hear it, or?
I'm just worried about my cat. Can you guys hear it?
I can hear it. I can hear it.
Okay.
You can't make it louder, right?
No.
You can't make it.
I made it
Okay.
loudest.
What we might try to do is like while people are doing their things, I will maybe try to have you play it from here. Maybe
Okay.
there's a way, but you might need a special software to do that.
All right. I don't.
We can try to see if there's any way to have the projector go up or something like that.
I'll play a little bit more, maybe. Is that okay?
Okay. And in the meantime, so she's our second or third person. So you're welcome to start photographing them as needed, and then we have to catch up with Daniel and Emma.
These are the ones I missed?
Those are I also missed Daniel because I forgot to, but we'll catch up.
Where she tried to do all these mathematical formulations to create violins, changing all the different violins to different sizes. But if you ask me, you can't explain it.
Next question.
All right. So, yeah. So that's the end of that
Beautiful.
question.
Like, watch it's 20 minutes. At the end of it, I was in tears. I mean, it's just literally this guy has such a inner understanding of geometry. Like, he doesn't even think the way like he would do mathematics, but he has such a good understanding of it that it was just wonderful. So this is one of the things I'm hoping it will be on the website, maybe at least a clip of it. Okay. So why don't we make this available, like wherever you're standing, so people will come to you. Who else needs to present it to everybody else? Is there anybody else? I know Theodore is going to actually, it would be nice at one point, maybe we sort of circulate towards Theodore. Do you need everybody, or could you do it one by one? How about you give at least a general shot to everybody, because there's so much stuff in your project that there might not be. It might be wise to just do it. So how about this? Did you already send me some stuff?
Yep, I sent you a file.
Okay. So let's actually do this. Let me have you also, if you want to sit here and present whatever you want to do, let me just open your file and then let's see. Who else? Farrell, are you doing general or?
Well, I don't really need to explain it or anything because people can just walk by.
People can just walk by. Okay, that's easy enough. So let's have. I especially want you to show the pentagon one at one point quickly.
Okay.
Because that's dynamic, people won't be able to see it.
Daytime TV.
So Stephen Binzu, demo day, is it here?
Yep, it's the one I sent you.
He's a cool guy.
Oh, in several parts, okay. So whenever you're ready, just give me a thumbs up. Okay. Things, the sizes may not work out, so we'll see what we can do about it. Who else needs everybody else's attention? How about you, Sam? Do you want to show that cube, dynamic cube, to everybody? I really want to show that to everybody, and then you could show the other stuff too.
Okay, so
this give me thumbs up whenever you're ready.
You have 3 points, and how would you find the minimum amount of telephone wire that would connect the 3 points so that you can be efficient and not spend a whole lot of money? So what we do is we build what's called a Steiner tree, just by putting an equilateral triangle on this face and another equilateral triangle on this face, and then we connect the opposite vertexes. So we connect vertex A which is the original triangle, to the opposite vertex of the triangle we just created, and then so there was a point that got constructed out in the middle here. That's what's called the Steiner point. And then you just connect those two. Oops. It's really didn't work. So you just connect them, and there you go. And this point is special because it forms a 120-degree angle. So this angle here is 120. This one's 120, and this one is also 120. But how do we know that it's actually the minimum distance, which is in this instance that? If you rotate it 60 degrees, the red and the green segments, then we know that, so we have this, and then if we connect those two, we know this one is also, that these are congruent because this is 60 degrees, and then that and that are congruent because there was a rotation, and so we have an equilateral triangle. So now we know that the purple and the green and the red are the minimum distance for this particular triangle. Now you can do...
Okay. Let me just remind people, do you remember the Aunt and River problem we did? The whole task there was, how do you linearize a broken segment? Do you remember that? So basically this is now linearization of the 3 point. So he basically came up with a method of linearizing 3 non-collinear things. And when you do that, you end up actually with a 120-degree partition of the area. Yeah.
You can do the same thing for quadrilaterals. Once again, you put equilateral triangles on 2 of the faces. So we have an equilateral triangle there and another one there. And then we connect the 2 points we just created. And we can inscribe the equilateral triangles, and we know that all the points along this arc right there are going to form 120-degree angles. So where it crosses those 2 arcs is where our magic points are going to be. And once again, if we rotate it out 60 degrees, we can see once again that, well, the colors didn't work out, but you could see that once again the quadrilateral has been linearized. Okay, for a pentagon it's a little bit harder, but you know, you can, it's the same general concept of we have 5 points now and we want to linearize them, and so we can have it move around. And then eventually it'll come to what's the minimum distance. And you know, once again, all 3 of those angles are 120, all of these are 120, and all of these are 120. So
let me make a comment here. There's a button in Sketchpad which is very rarely used. Even people who use it, they just use it for demo purposes. Okay, it's called the movement button, in which basically a point chases another point. You're basically teaching a point to how to follow another point. So what we discovered in this process is it is possible to, in this pentagonal construct, to have the points chase each other until they cannot move anymore. So they basically stabilize, and that's basically your Steiner construction, which is really amazing. I mean, it's sort of like, we don't know what the solution is, but we know, we teach exactly what point to chase what point. Do you have anything like show hidden? What is behind that? Display show hidden. Let's see.
just a lot of points.
Just a lot of points. Okay, so that would make sense. But basically what's happening is we have these 120 Y letters. Think about 120s. They're chasing just the right thing, so when they stabilize, they cannot move anymore. That's the Steiner construction. So which is a very, like, it proved to be an incredible technique. We were able to go all the way to the decagon in the course of a week, where we were stuck for like a couple of months, you know, we couldn't make any progress. Okay, so this is, I think, a good enough introduction, and then on the poster, hopefully things are going to become clear.
Right.
Say something.
So, did my project on the elliptical machine, and basically improving that this machine, which is supposed to make your feet go in an elliptical motion, doesn't actually do that. And it actually makes your feet go in like a weird shape.
I just made a cube on Sketchpad, and then I animated the points, so it's just like it's working. It's awesome.
It's basically Vasarely in 3D. I still don't know how she did it, because there's all these it's randomization, right? There's some kind of a random. They're not moving in a predictable way. Is it just random?
They're moving back and forth.
Can you show us all hidden, just out of curiosity, so we have a sense what goes into this? So a lot of parallels and perpendiculars.
Yikes. Okay.
Beautiful. Anything else?
Feel the force.
Come on. So this is basically what you're doing is there's an ellipse. If you mount an object on an ellipse, it gives you the illusion that the object is tilted. So you could always, like, once you have the ellipse as a base, you could distribute evenly, like, points, in this case, 3 points, and then the top point you could even arbitrate. Okay, can you move that upper segment so we can show how you could decrease the size up and down? So that's not too hard. And then the other construction, the hypno triangle you have done. All you have to do is make it as a script and then just go from side, 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 and it's basically covering this. So even the idea is not, amazing, but when you do it, it's pretty amazing. It just looks, things are overlapping and so on and so forth. When you're watching Rastow's work, ask him to stop the Eiffel Tower, because when you stop it, everything so overlaps. You don't see the structure. You don't even recognize it. But when it starts turning, you start understanding that it's a 3D object. Anything else that you want to discuss?
So this is my project on model the platonic solids sort of in 3 dimensions on the computer using Geometry Sketchpad. And what's interesting, what I find most interesting about this project is that we're using regular construction-based Euclidean geometry to deceive into thinking we're working in 3 dimensions, when in reality we're only working in 2.
Okay, so my project was origami, and I basically made this. Stop watching. Okay, I made this with a bunch of these, actually 60 of them. Okay, sorry.
Good.
So it took a long time, and basically the way you make these is shown in here. You go all these different steps, and it takes a while. And so then after I made these 2, they're all made out of this. I made a bunch of other just origami stuff.
Okay, so basically I did my final project on fractals, and I did a lot of different things. Basically fractals, a lot of the fractal shapes I did have an infinite perimeter but a finite area, and you can see them in these shapes where you just keep iterating self-similar things onto different shapes. And then I had a lot of fun with it. I made some of my own stuff up, like flowers that have fractal sides with this pentagon fractal, because for the Koch snowflake you make basically a line with an equilateral triangle off it, and that's what you iterate onto all the sides, and basically I experimented that with a pentagon.
Go.
I decided to do optical art for my project because, first of all, I love art, and just the hypnotic qualities of optical art I think are amazing because you don't need technology to do them. You can just sort of do it yourself. And also that there's so many different types and styles and illusions that you can create with just a straight edge and some markers and such. And there's so many really, they all work into things like tessellations and, what's the other one? I forget the other one. But there's a lot of people like M.C. Escher and Joseph Albers and Victor Vasarely who did a lot of these things, and they're very famous now.
My project is geometry and architecture and nature, and I basically took photographs of architectural structures in Washington and around Concord, and then nature in various places, and just explored it through black and white photography.
Talking and then, yeah.
So this is an imitation of one of Andy Goldsworthy's whole constructions, where there's a hole in the middle, and then the surrounding pieces of nature kind of change colors or change shapes. And so this is about the middle spring, when there's flower petals in the middle and then dried leaves on the outside, because that's what you see in spring.
Beautiful.
All right, the purpose of this project was to investigate the Eiffel Tower and see how it's affected, how geometry speaking, it's able to work and able to stand upright, because when it was built, or when it was beginning to be built, nobody thought that just a building made out of iron, pretty much segments and connectors, would be able to stand upright, because it shouldn't be. But because of congruent triangles, which are formed up and down the sides of the tower, and the angles of the congruent triangles pretty much force the sides of the tower to be together and be upright.
Okay, well, my project was on geometric art, so I did a little sample of everything. You can see on the poster. These are...
Look at me.
These are some cycloids I did, and then I have some hypnotic spirals, and then these are some hypnotic spirals that were animated and they move away, so I put them out. And then this is a cube and a pyramid and a dodecahedron that move around, and I put hypnotic spirals on their sides. And then this is an optic art cube, and these are just the S-rays.
There you go.
The altitude is the geometric mean of the part and part.
The other one. And the other one. And the other one.
That was good. The leg is the geometric mean of the part and whole.
Wow.
In the hotel room that
He's like
funny at night.
he's a sexy dancer.
He is a good dancer.
Yeah.
No.
So, what Java Sketch is, it's basically a program that uses Java. So people who don't have Geometry Sketchpad are able to use and view Geometry Sketchpad files. It's still very, very basic. Like, there are a lot of things that you can do in Geometry Sketchpad that you can't do in Java Sketchpad, but there's still a lot of interactivity. Like, you can select points and move the sketch around, and it's very just amazing.
Yeah.
Hi, I'm Arlena, and I did a project on the study of damage in geometry and architecture. And I was looking at 3 different figures to study this: the hexahedron, the cube, and the tetrahedron. And my hypothesis was that the tetrahedron would survive a test of damage the best because 3 points define a plane and it's the most sturdy. And I proved the hypothesis right. And these are the before models, and these are the after.
Something like the Sierpinski triangle, you're gonna have to do it yourself by hand. And so you can flip this around and stuff, and you can make it stop rotating. And then here's another one that's basically just kind of the same. It's taking a while because like there are a lot of actions in this, which makes it a lot bigger, so it won't rotate for a while.
That was one that was not actually done by iteration, so that's why everything is shown.
It wasn't done by iteration, but so it wasn't done by iteration. So JSP didn't take it out when it was being converted. So here's a lot of stuff. Like it's moving now very slowly because the internet's kind of slow. And then down here's a dodecahedron, but here it is, and you can rotate it. Yeah. And so basically, it's really easy because all you have to do is have, when you have Geometry Sketchpad, in the CD, there's basically a file that says JSP, and you just copy that and paste it onto your desktop or wherever you want to put all your JSP files. And then when you're in Geometry Sketchpad, what you do is when you're
show it.
All right.
People will not remember all this detail.
Okay.
Definitely you can show the Sketchpad version.
All right.
Tom.
Okay, so you could publish on the web this summer. I mean, all this stuff you've already done.
All right.
Figure out which ones you can already post.
So we'll just make like a triangle. And then what you do is you go File, Save As. Well, first you want to like save an original copy of the GSP file. So like you can always go back and change it if you like don't know how to program, because it's really difficult to program these. And then you go to Save As, and you save it in a Sketchpad folder with this file. It has to have JSP. But I'm not gonna. Is it okay if I save it in here for right now and delete later?
Is that, I don't know if it's going to allow you to do it, but
It might.
definitely try. You can't do that. It's GSP. You have to make it HTML. Yeah.
And so you select HTML/Java Sketchpad document, and we'll just be like, try, and then save it, and then you can preview it in your browser. And it just takes a little bit while to load, and you can like move it around and stuff. When you're saving it, you can make it be different sizes. Like